Welcome to Chemistry Online. Today we're going to talk about acid-base equilibria, and we're going to speak about strong acids and weak acids. A strong acid, HCl, nitric acid, sulfuric acid, they dissociate essentially completely into ions in solution. Now, if we write an expression for the equilibrium constant for this, again, we're going to ignore the water, and we're just going to have hydronium chloride and HCl. If we have essentially complete ionization, hydronium and chloride will be large, and HCl will be very, very small. That makes Kc here, based on concentrations, very, very large. For acid dissociation, we're going to change Kc to Ka, where A stands for acid dissociation. Now this is a strong acid. In a strong acid, Ka is very, very large. Let's look at a weak acid. Here we have acetic acid. In acetic acid, we have very little ionization. So hydronium and acetate are very, very small. Our equilibrium expression looks like this. Again, we don't include the water because it's heterogeneous equilibrium. Hydronium and acetate are both very small. Acetic acid is very large, making Ka much, much less than 1. In fact, for acetic acid, Ka is 1.8 times 10 to the minus 5. Now let's take this and let's apply it to a problem. Here's our value for Ka for acetic acid. I have acetic acid in water, and I measure and I found my hydronium ion concentration to be 4.2 times 10 to the minus 3. What is the concentration of my unionized acetic acid? First, I'm going to write an equilibrium expression. One thing you have to note, though, is that every time you ionize an acetic acid, you're going to form 1 mole of hydronium and 1 mole of acetate. So these guys are always present at equal concentrations. Here's our expression. Again, we leave out the water. These two are identical. Now we've measured hydronium, so acetate must be the same. And all we have to do now is solve for acetic acid concentration. We do our simple math, and this is equal to 0.98 molar. So what have we proved here? In this calculation, at equilibrium, we have 0.98 molar acetic acid and 4.2 times 10 to the minus 3 molar hydronium and acetate. Again, it is virtually entirely unionized. Let's look at a different type of problem here. Here I'm going to take 1 molar acetic acid in pure water, and I'm going to estimate the pH. Now, I'm going to set up an ice table with my initial equilibrium and change. I'm going to do this assuming that no ionization has happened initially. My change is going to be in a value x. What I'm saying here is that a small amount of acetic acid is going to ionize. When it does, it will drop the concentration by x. As it ionizes, it will form hydronium and acetate, and therefore they will increase by x. At equilibrium, I have 1 minus x, x, and x. Now let's take our equilibrium expression and let's substitute. Each of these is equal to x, and this is 1 molar minus x. Now this expression as it sits is a quadratic. We could solve it with the quadratic formula, but we can take a shortcut here. We know that this is a weak acid, so X, which is hydronium, is going to be very small. It's going to be much, much less than 1. Therefore, 1 minus X is essentially going to be 1. Now we can take the equation and rearrange it. X is approximately equal to the Ka, that's 1.8 times 10 to the minus 5, times our concentration, which we said was 1 molar, or 4.2 times 10 to the minus 3 molar. Now, the problem actually asked for the pH, so this is our hydronium. We know that pH is minus log hydronium, and this is 2.38 as our pH. Now, what we've done here is called the weak acid approximation. Basically, you can estimate hydronium if you know the Ka and the initial concentration of your weak acid. Hydronium is equal to the square root of Ka multiplied by our concentration. As long as the concentration is 100 times greater than the value of Ka, this is a very useful approximation. Let's look at this in a tutorial. Here we have lactic acid, and this is its Ka. Our concentration is 0.097 molar. Our weak acid approximation is just going to take the concentration, the Ka, and we're going to take the square root. When we do this, our hydronium ion concentration is 8.81 times 10 to the minus 3 molar. In order to get a pH, we simply need to take its negative log. Our pH here is 2.08.